Welcome friends, Igor is here, and in this video we will define the notion of a basis of a vector space. In this lesson we will define a basis of a vector space, we will construct bases for several vector spaces, and we will find connections of bases with non-singular matrices. Let's get started. The idea of a basis of a vector space is simple. A basis of a vector space V is a set of vectors in that vector space, which is, first of all, linearly independent, and secondly, spans the entire vector space. In other words, a basis of a vector space is a linearly independent spanning set for that vector space. Let's prove that the set of standard unit vectors forms a basis for the vector space of column vectors. To prove that this set is a basis, we need to show that it is linearly independent and it spans the vector space of column vectors. The linear independence of this set is easy to see. The standard unit vectors are the columns of the identity matrix. The identity matrix is a non-singular matrix, therefore its columns form a linearly independent set. To prove that this set spans the vector space Cm, we need to show that every column vector from Cm can be obtained as a linear combination of the standard unit vectors. And there is an obvious way how to decompose any given vector into a linear combination of the standard unit vectors. An example of a basis for the vector space of polynomials of degree at most n is the set of monomials. I will leave it as an exercise to check that this set is indeed linearly independent and spans the entire vector space. In fact, each vector space has many different bases, and here's an example of another nice basis for the vector space of polynomials. Again, please check that this set is linearly independent and spans the space Pn. Here's an example of a basis for the vector space of matrices of size m by n. This basis consists of the set of matrices B sub KL, which have the following property. This matrix has all zero entries except in position KL, it has value 1. There are m times n such matrices, and they do form a basis of the vector space of all m by n matrices. Please check that this set is indeed a basis. Here is an example of what these matrices look like in case of the vector space of 2 by 2 matrices. In two previous lessons, we proved that the following set R of two vectors from the crazy vector space C is, first of all, linearly independent, and secondly, it spans the vector space C. Therefore, by our definition, this set is a basis for the crazy vector space. The notion of a non-singular matrix runs through most of linear algebra, so it is not surprising that there is a direct connection between the new notion of a basis and non-singular matrices. Suppose we have a square matrix A of size n. Then the columns of this matrix form a basis for the vector space Cn if and only if the matrix A is non-singular. This is an if and only if statement, so we need to establish two separate implications. In the forward direction, we are going to assume that the columns of the matrix A are a basis for the vector space Cn. A basis must be linearly independent, therefore this means the columns of the matrix A form a linearly independent set. But this implies that the matrix A is non-singular. In the opposite direction, we are going to assume that the matrix A is non-singular. Then the columns of A are linearly independent, and the column space of the matrix A is all of Cn. But the column space of the matrix A is the span of the set of the column vectors of A. So this means that the columns of the matrix A span Cn. We see that the columns of A are linearly independent and they span Cn, therefore they form a basis of Cn. This discovery means that we can extend our list of equivalent properties for a non-singular matrix. Now we know that a matrix is non-singular if and only if its columns form a basis for the corresponding vector space of the column vectors. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will define the notion of the dimension of a vector space, and we will compute the dimension of several vector spaces. I will see you later.